Okay, in this video we will be talking about bit manipulation, and when asked in an interview as a coding question to add two numbers without using a plus sign and then identify whether that number is odd or even. Now this would be pretty basic. Now this would be a pretty basic question and could probably be done in a few lines of code, but the catch here is to not use the conventional operator signs. And in this case, we can't use the plus sign or the modular sign. So we first talk about base 2 and how to get an integer in a binary form. Then we will briefly discuss all of the bitwise operators so you can get an understanding of what can be done with bit manipulations. Then we will manually add some binary numbers, check to see if they are even and odd, and to develop some pseudocode, and finally write some code to get the solution to our question. So let's first start with talking about binary code in base 2. So whenever you get a question regarding simple mathematics, you know it isn't going to be that easy. When you are not allowed to use conventional operators, you should automatically think about bit shifting or bit manipulation to produce the results desired. Bit manipulation is the act of algorithmically manipulating bits. Some tasks that use bit manipulation include some low-level device control, error detection and correction algorithms, data compression, encryption, and of course optimization. In some cases, bit manipulation can reduce the need to loop over a data structure and can give a huge decrease in time complexity as bit manipulations are done in parallel. But keep in mind that the code can get pretty hairy and become difficult to write and maintain. You always have to weigh out the variables in optimization. Let's see how a number is expressed in the computer. So in a base number system, it has the base to the power in the position that I'm sitting in. When added up, will give me the actual number. So if we have a 13 here and wanted to express this using a base of 2, we can see that all of the bases here are 2, and the exponent represents the position. So here's the first position, 0, the second position, 1, third position, fourth position, fifth position. Right? So we have 0, 1, 2, 3, and 4. Now, when we calculate these exponents, we see that we are given a value for each empty line. So let's do 2 to the power of 0. We know that will be 1. 2 to the power of 1 will give us 2. 2 to the power of 2, 4, 8, and 16. Looks like a lazy 8. All right, and this could go on for quite a bit. Then we have to ask ourselves, moving from left to right here, how many 2 to the power of 4s does this contain? Well, 13 does not have 16 within. Remember, we will add up all of these later, so we will place a 0 in this place. Put the 0 here. Next, how many 2 cubed does 13 contain? Well, we have 8, and that would make up a 13, so we place a 1 in this place because we want one of these 8s here. So when we subtract 8 from 13, we're left with 5. So within these remaining spaces here, we want to get a 5. So let's ask ourselves, how many 2 to the second powers, or 4s, do we have in 5? Well, we definitely have 1. Now we want to subtract 4 from 5 here, and we're left with a 1. So then we ask ourselves, do we have any 2s in this one? No, so we're going to have a 0. And lastly, we have that 1. We need that 1, so we will put a 1. So now we have successfully encoded a binary form of 13 with the help of our understanding of base 2. Now we can always express different numbers in different codifications using different values in different places, but to not confuse you so much, we'll just run with this. All right, that was the first part in understanding the problem. Next, we have to get an understanding of bitwise operators. I'm going to talk about all of them, but in our question for this video, we're only going to be using 3 of them. It's just a good idea to review all of them, just in case you have to use them elsewhere. All right, so we have 6 different bitwise operators in Python. We have the complement here expressed as the tilde, the AND operator expressed with an ampersand, the OR operator expressed with a pipe, XOR expressed with a hat, left shift and right shift using less than or greater than signs. Need 2 of them. Let's talk about the complement operator first. This isn't used that much, but can get us to an understanding of negative numbers in binary form. When we input a tilde with a 12, we will expect the complement of that number. So what is a complement? So when we hit enter, we get an output of negative 13. That's a little odd, right? You were probably thinking you would get something different. When we ask for a complement of 0, we get a 1. So for 0, we'll always get a 1. And for a 1, we'll always get a 0. So this is what is going on under the hood. Let's take the binary form of 12. We're going to switch all of the 1s to 0s, and all the 0s turn into 1. So the complement of 12 will equal 1, 1, 1, 1, 0, 0, 1, 1. Now that doesn't look like a negative 13, does it? It's because the system does not store negative numbers. It always stores positive numbers. So if we wanted to store a negative 13, we would have to store it as a positive number first. And the way that we do that is with the help of 2's complement. So 2's complement is 1's complement plus 1. So we'll say 1's, let's say 1's complement, and then we're going to add that to 1. So that's the formula we use for storing negative numbers. Let's encode 13 as a positive number. We get, if we look at 1's complement of 13, so now let's take the complement of this, say 1, 1, 1, 1, 0, 0, 1, 0. And we're going to take that now and we're going to add a 1 to it. So all we're going to do is add a 1 here. Now because we added a 1 here, the 1 is now 2's complement of 13, and now it represents a negative 13. So when we add this to 1, we're going to get 0 plus 1, 1, 1, 0, 0, 1, 2, 3, 4. Now let's compare the result. So here we have 12, and let's express this as a binary form. So we'll get 3, 4, 1, 1, 0, 0. Now we want the complement of 12, and we're going to get a 1, 2, 3, 4, 0, 0, 1, 1. Now this negative 13 and this complement of 12 are the same value, the same binary number. This is why our complement of 12 arrived at negative 13. I recommend you play around with some numbers, do some manual encoding to put numbers into a binary format and find their complement. Then you can get a good understanding of what is going on with the complement operator and how binary numbers are represented in the system. Bitwise AND operator is the ampersand. That's because the conditional operator uses the word AND in Python. So if we look at the output of 12 and 13, we get 12. We know the binary format of 12 is, and the binary format of 13 is. Think about AND in a conditional statement. Remember, both values have to be true in order to have an output of true in a conditional statement when you use AND. So if you have a 0, let's say a false, and a 1, which is true, using an AND statement will give you a false or a 0. So this is what happens when we compare these two numbers using an AND bitwise operator. We're going to use an AND, or let's say an ampersand here. So comparing the 0 with the 1, we don't have both values as true. So we're going to put a 0 there. Here we have both values as false. So this will also be a 0. We have a 1 here and a 1 here. Therefore, this will be true, or it will be 1 because we're comparing with the AND statement. Here's another true value here, and all the rest are just zeros. You can say all of those are false. So if we made a statement with 12 or 13, let's see what the outcome will be. So here we have a 0 or 1, and one of them is true. So we'll have a 1 here. None of these are true, so we'll have a 0 here. Both of these are true, so that means we'll have a 1 here and a 1 here, and the rest just get zeros. All right, looking at the binary representation of this number here, we can tell that our outcome is going to be 13. So let's go ahead and check this in Jupyter. So before we said 12 and 13, and our result was 12. So now let's do 12 or 13. And we are hoping to get 13, which we do. We have a correct calculation. Let's look at one more example so you can see that the numbers will change. So if we input, let's say, 25 and 30, we get an output of 24. So play around again and manually convert and use OR and AND to check your output. Next bitwise operator we'll talk about here is the XOR or XOR. It's usually pronounced XOR and signifies an exclusive OR statement. Meaning if I had two numbers and I was comparing using a XOR operator, I would get a 0 for comparing two zeros. So if I compared a 0 and a 0, I would end up with a 0. I would get a 1 when comparing a 0 and a 1, or a 1 and a 0. But when I compare a 1 and a 1, I would get a 0 because we are talking about exclusivity. So we will get an output of 0. An easy way to remember this is if you have an odd number of ones being compared, the output will be 1. If you have an even number of ones, like here, our output will be 0. Let's look at the output of 12 XOR 13. Here we get an output of 1. Let's manually calculate the XOR statement that we compared on Jupyter using these two numbers. Let's see what we're left with here. So we want to compare this first column here, so 0 or 1. That's good, so we'll come out with a 1 here. 0 or 0, we'll come out with a 0. 1 or 1, remember that this is an exclusive OR statement, so we're going to end up with zeros here and zeros just in front. So here we're left with just 1 as our output. Now left shift. All right, we're going to use two less than signs, and let's go with a 10 with a left shift of 2 bits. And here our output is 40. So why 40? When we manually calculate 10, we end up with 4 zeros and a 1 0 1 0. Then a left shift operator of 2 will shift 2 bits to the left. So here if we're doing 10 with a left shift of 2 bits, we're going to shift this over 2 positions. If you think about it like this, every number can be represented with a decimal point behind it. Let's say if I had a 5, we could put a load of zeros behind it, and it's still going to equal 5. So same thing can sort of be said about the binary representations. We have a block here to represent a 10. If we added a decimal point to the end, so let's say a decimal point here, and let's just add a bunch of zeros here. Now when we shift 2 bits, we are just going to move these ones and zeros 2 places to the left and then fill the empty spots with 0. So if we shifted 2 spots to the left, we would say 1 0 1 0 0 0. So let's take this number here and check to see if it equals 40. So let's identify these positions here. We have 6 places within this binary representation, and we're going to start with a base 2, 2 to the 0 power, 2 to the first. All right, so let's calculate what these values actually are. We'll go ahead and start with 2 to the power of 5, which is 32, 2 to the power of 4, which is 16, 8, 4, 2, and 1. Now we want to see if this is a part of 40. So let's just take 40 and go ahead and put this 40 into binary form, and then we'll compare the two representations. So we have to ask ourselves, is there a 32 and 40? Yeah, I would definitely say so. So we're going to put a 1 here, subtract 40 from 32, we're left with 8. So now in these remaining spaces, we want to try to get an 8. All right, so we ask ourselves, is there a 16 in this 8? No. Therefore, we're going to put a 0 in this position. Well, here's the 8 that we need, which will make all of the remaining positions zeros. So when we compare this value with this value, we can see that it is the same. And this is how the left shift works. So keep in mind, with a left shift, we are gaining bits, but with a right shift, we are going to lose bits. So looking at a right shift of 10, we'll do a right shift of 10 using 2 bits. Here we're going to go to the right, 2 bits. So looking at a right shift of 10 by 2 bits, let's start with the binary format using just 4 ones and zeros. So 1 0, 1 0. And we're going to exclude all of those zeros in the front because they have no effect on the value. Now we're going to shift 2 places, and we are going to be left with, so remember, we're going to shift, pretend like there's a decimal point there. We're going to shift this over 2 places, and we're left with just a 1 and 0. The other 1 and 0 here were excluded as they fell past that decimal point. Let's add some zeros in front just to give you a good idea of what we're looking at here. What number do you think this could be? All right, remember in our base 2, this number here is going to be equal to 2. Let's go to Jupyter and check that out. So here in Jupyter, we're going to say 10, and we're going to right shift this 2 bits, and our output will be 2. So that's what the 6 operators of bit manipulation do. Now let's talk about adding up some binary numbers and what this will look like in our function to add 2 numbers without using a plus sign. I'm going to add up some numbers in base 10 so we can get a good understanding of carrying. And those of you who are taught using Common Core math might not know how to do it the old-fashioned way. I don't know. I'm just kidding. But anyways, let's add up 123 and 39. All right, we're going to take this first column here. We're going to add that up. That will be 12, so we put the 2 here, carry the 1, add up these 3 numbers here. 3 plus 2 is 5, plus 1 is 6. And we have nothing to carry, no value here. Make it a 0, and we're going to say 1. Since we're familiar with adding base 10 numbers, let's utilize this same method of carrying over to base 2 numbers. Let's turn these into binary representations. So for 123, we'll have, and for 39, let's say 1, 0, 0, 1, 1, 1. All right, we're going to add up those 2 binary representations. Now we're going to do it the same, but with 2 slight differences. Because we are using binary form, we are not going to add up these 2 ones and write a 2. We're not going to add up, maybe if we carried 1, we're not going to write a 3. Remember, these 2 numbers are in binary form. So we have to remember that 2 is going to be a 1 and a 0, while 3 is going to give us a 1 and a 1. So when we add our two ones here, we're going to place the 0 here because 1 plus 1 is 2. So we're going to place that 0 here, and we're going to carry this 1 up here. Now when we add these ones, we're going to get a 3. Well, we're going to take that 1, carry the 1. Here we're left with another 2, so we'll put the 0, carry the 1, another 2, place the 0, carry the 1, another 2, place the 0, carry the 1. Here we're left with 3, place the 1, and carry this one. And now we're left with just, well, let's do it like we did before. 1 is 2, so we'll place the 0 here and carry the 1, and nothing to add up with, so we're just left with 1. So as you can assume that this binary representation here is actually going to equal 162. All right, so we used that same idea of carrying that we used with our base 10 numbers. Now we have used the plus operator. We have used a carry method for shifting some stuff over to the left. And you can see where this is going, all right? We have our bitwise operators that we are going to be working with to utilize this method within our system using Python. So if you think about it, we will be using the ampersand. We will be using the AND operator, the ampersand, the hat, right, the XOR operator, and finally we're going to use the left shift, right, the left shift, less than sign. Right, so the AND bitwise operator, this is going to find all of our carries, all of these carries that we had to do when we manually made this calculation. Next, the XOR operator will do the actual adding. So we'll say that we'll do the actual adding. And last, we're going to use those the left shift operator, and we're going to say that left shift operator will use the carry within the next iteration. So I'll explain that a little more, but let's just say shift the carry, because after all, we can't use that carry in the same column that we had just calculated. So we're going to have to left shift this carry. So thinking about this function and how it's going to work, we're probably going to be given two variables. So let's just call this variable, the first variable A, and we'll call that second variable B. And what these variables are going to do is A, let's say A is going to hold, it's going to hold all of the running calculations. Well, let's say all of the running addition. Be a little more specific here. Remember, we work from left to right, so each column or iteration must be held as we go. And then B is going to hold all the carries. So B, let's say we'll hold the carries. So first we're going to have to find the carry positions. And the next thing we'll probably have to do is do the addition. And the third thing we'll have to do is make a shift. So let's write these down as the steps. So first we're going to have to find the carry positions. Next we'll do the addition. We'll do the actual addition. Let's say actual. And lastly, let's do that left shift for the carries. All right, so I'm just thinking about some pseudocode here. I like to put everything in steps so I can sort of follow in order and kind of follow the road that my mind is processing. So thinking about it, we will add A with B, and as B holds the carry in each iteration. And if you think about it, we're doing all of the addition, all of the iterations at one time. And this is our parallelization we talked about earlier. Let's just do a manual walkthrough here to see what we want to occur. A and B will be my parameters in the function. I'm adding two numbers here. So let's say A is 1 and B will be 3. Now we're going to add these two numbers without using the plus sign. Let's take a look at their binary form. How does it look within the system? 1 is represented as, and 3 is represented as. All right, so remember the first step here. What we're going to do is we're going to find where we need the carries. And we'll be doing this with the ampersand operator. Let's go ahead and throw it in just to remind us here. Here we have the ampersand. Here we have the hat for the XOR, the actual addition. We'll see how it comes later. And a left shift, just to keep those symbols in mind. All right, so we're going to find the carries of these two numbers. Now, what we're going to do is we're going to compare these two using an AND operator. So when we compare using the AND operator, remember 1 and 1, we have a true. 0 and 1, this is going to be a 0. Here this will also be a 0, and this will also be a 0. So we're left with just 1. So we're going to take that number and let's just put it on the side here for now. The next step is actual addition. So let's compare using our XOR operator. So we'll compare the 1s. Remember with a XOR statement, it's an exclusive OR statement. So 2 1s are going to give us a 0. Then we have a 0 or a 1. We're going to say that's a 1. Zeros and zeros give us all zeros. So let's take this number again and we'll put this to the side. All right, so remember with these two values here, we don't want to add those up with our raw carry. So we need to left shift this. We're not going to add our carry where we found it, right? So we need to shift it one position over to the left. So let's shift this and put this into variable B. All right, so we're going to take this value here and we're going to apply a left shift method with only one, moving a left only one position. So in that case, this 1 will be in its second place here, and we're left with, say, 0, 0, 1, 0. Now we had the carry and we shifted it left, and now this will become the variable B. Now let's take this second value that we put to the side. Now this is our actual addition here, right? And if we remember correctly, our A is holding all of that actual addition. So let's go ahead and put this under here. So we'll say 0, 0, 1, 0, which is equal to A. And now we start again. All right, in the second iteration now, our first step, find all of the carries. So we're going to use that AND operator, and we're going to find the carry. So here we have 2 zeros. When we compare it, we get a 0. Here we have a 1 and a 1. Output will be 1. And for these two columns here, our output will be 0. So we're going to put this off to the side, doing our next iteration, because we have to apply another left shift to this before we actually put it into our variable B. Now let's complete our second step. We're going to do some actual addition here using the XOR operator. So 0 or 0 will be 0. 1 and 1, this is a XOR statement. So this will also be 0. And we have some zeros here. All right, so our running total for now will be all zeros. Now we're going to do our third step here. So we're going to do the left shift for these carries. So for the carries, we have a 0, 0, 1, 0, and we will apply a left shift of 1 bit. Now we have 0, 1, 0, 0, and this will be our B variable. Next, that running total will be our A variable, and we'll throw in all of the zeros here. All right, next iteration. So let's start with the first step. First step will be to find all of the carries. Now, we're going to use the AND operator. So 2 zeros will give us a 0, another 0. We have a 1 and a 0. Now this will provide us a 0. Now this is also a 0. So let's just put that over here. Now let's do our second step, actual addition. All right, we're going to be using the exclusive OR statement, the XOR statement, or the XOR operator. We have 2 zeros, leave us a 0. These zeros will leave us a 0. Here we have a 1 or 0, 1, and left with a 0 now. Now, we didn't have any carries, and therefore if we performed our third step, our left shift for these carries, nothing would happen. It would just remain 0. So that's it. We can't do anything else. So we're left with the solution to this problem as 0, 1, 0, 0. So let's figure out what this equals. So if we look at the base 2, so this is to the third, 2 to the second, 2 to the first, and 2 to the 0 power. So I'll write the values here just to give us an idea. So here's an 8. In this position we'll have a 4. This position will have a 2. And in this position we'll have a 1. So thinking about this, we only have a 1 in the second position. So this number here is going to actually equal 4. All right, and going back, simple mathematics, 1 plus 3 is going to leave us with 4. So this will be the solution to our addition problem. All right, now we have the steps in our code. The 3 steps, all we did was use the ampersand, we used the XOR, and we used the left shift operators to help us arrive at this conclusion. And that's it for our addition part. We arrived at our sum of these two integers, so let's move on to the last part of the question. So the last part of this question was, is this number even or odd? So I'm going to write this 4 here, just to remind us what our solution was to that addition problem in the last part of the video. So is this number even or odd? Now we can't use the mod sign here, so let's do some bit manipulation to find out if it is even or odd. I want to first take a look at the numbers 0 to 7 in binary form. So let me just write these out. So if you look at these binary representations here, you'll see a pattern. The odd numbers all end with a 1, and all the even numbers end with a 0. So logically, we can accept 2 observations from this table. The first is that adding 1 to an even number will make the sum odd. If we added 2 with 1, we would get 3, right? So the 2 would be a 0, 1, 0, and we're going to add this up with a 1, 0, 0, 1. 1 plus 0 is 1, 0 plus 1 is 1, 0 and 0 is 0. The second thing here is adding any even number with another even number will result in an even number. So let's say if we added 2 and 4. So 0 and 0 is going to be 0. 1 and 0 will be 1. And 0 and 1 will also be 1. So 4 and 2 will give you this 110 for the number 6. So in our column here, we will never end up with a 1. We are just adding zeros. And we will never have a 1 in the mix. Now let's look at an example. Whenever we use the AND operator, when comparing a number and 1, we will either get a 0 or 1. So taking 3 in its binary form and 1 in its binary form, let's compare the two using AND. So here we have a 1 and a 1, so that will give us a 1. Here I have a 1, 0. We're using AND, and that will give us a 0. And we have another 0 here. So in this case, this will give us 1. Let's compare another one. Let's compare 6. So we'll do 1, 1, 0. And we're going to compare that with 1. So 0, 0, 1. We're going to use the AND operator. So here we have 0 and 1. It gives us 0. Here we have a 1 and 0. Gives us 0 and another 0. So this will give us 0. So we can say it will give us a 0 if even, and a 1 if it's odd. 3 was odd and 6 was even. We need to add this into our code as well. Now that we have the pseudocode sort of written, let's get to our function to finally write some code that will give us a solution to this problem. So let's define a function here. Let's call it sum, odd, even. Define a function with two parameters, a and b. Let's get back to our steps that we're going to implement. Step 1, we should remember this. We're going to implement step 1 and to carry. Step 2, the XOR to do actual addition. And 3, left shift for the carries. Now, let's not forget that a as a variable will hold our running additions, and b will hold the carries. Now we're going to do an unknown amount of iterations here, so we can utilize a while loop for each iteration and make it end once we have nothing more to carry. So in other words, while b is not equal to 0. So let's go ahead and fill this in. While b is not equal to 0. Now within this while loop, we need to execute our steps. I think this was perhaps the trickiest part of the problem. To get a solution, you have to use multiple assignments due to the operation of Python under the hood. It's an explicit language and will not arrive at the correct solution if you were to separate or separately assign A and B on different lines. Let's take a look here. So we have to assign A and B on one line to their respective operators. A will hold the running addition and therefore uses the XOR operator like we have here. And B holds the carries. But see how we sort of separated it in the steps that we had? We said this third step would left shift for the carries. So we need to combine these steps. 1 and 3 need to be combined. So we can take the carries, we can find the carries, and then we're going to left shift that as soon as we find all the carries. Now that's all for the addition part. Now for distinguishing odd or even for our sum, all we have to do is use the AND operator with 1 as we've seen. So we will create an if statement saying if the output of A and 1 is 0, then the answer is even. So let's see how this looks. And conversely, if the output of A, we could say else, if the output of A is not equal to 0. Then we can print A equals to A, which is an odd number. So when we visualize this using Python Tutor, we can see the values being compared. Oh, first have to call that function. So let's see how these values are being compared. Now, if you really want to get a good understanding of how this code is working, I would suggest doing the manual calculation of the two numbers you are adding and check each one of your calculations with the output that is shown here. Now let's run through this code here. And we can see those values changing for A and B, our running total, and our left shifted carry. And to finish it up, we get an output of A equals 4, which is an even number. So just to check it, let's put some other random numbers in here. Let's say 6 and 7. This will be an odd number. We can visualize that execution again. And we are left with A equals 13, which is an odd number. So that's it for this video. I hope you have a good understanding of bit manipulation from this video and how to use this knowledge to answer some questions. Thank you and have a good day.